This presentation is a review of the viability of photovoltaics, or PV, based on current development data, trends and rates, and seeking to establish the potentials for building integrated photovoltaics, or BIPV. Such is the expected subdivision of the presentation, where the first part mainly focuses on the development of PV throughout the decades and in terms of production, installations, cost, efficiencies, and greenhouse gas emissions, whereas the second part reviews the current status of BIPV and explores their potentials in the building industry. A progressive rise of fossil fuel cost is affected mainly by a rapidly growing population, which henceforth resulted and will continually result to a rapid increase in energy demand, and thus rendering energy use to become a crucial concern in the past decades and the decades to come. Environmental issues caused by mismanaged or exploitative energy use has caused the devastating effects of climate change and global warming. According to the statistics released by World Health Organization, direct and indirect effects of climate change leads to the death of 160,000 people per year, and that the rate is estimated to be doubled by the year 2020. This has then led the world to explore other sources of energy so that we can depend less on those which are increasingly deteriorating. Renewable energy is a sustainable and clean source of energy derived from nature. Renewable energy technology, as described in Furkan's article, is one of the solutions which produces energy by transforming natural phenomena or natural resources into useful energy forms. Currently, conventional energy sources constitute almost 80% of global energy consumption. Renewable energy sources like solar, wind, biomass, hydropower, and tidal energy are promising carbon dioxide-free alternatives. Despite the general awareness of advantages of renewable energy utilization, these sources of energy contributed only about 1.5% of world energy demand in 2006. Among various solar energy technologies of sustainable energy sources, photovoltaics appear quite attractive for electricity generation because it is noiseless, it has no carbon dioxide emission during its operation, it has a flexible scale, and is rather simple to operate and almost free of maintenance. This illustration gives us a scale of how much energy is offered by the sun in comparison with other energy sources such as wind, biomass, tides, coal, petroleum, and natural gas. Undoubtedly, there is this much terawatts worth of resource that could potentially be tapped and utilized. In an article by Mekelev and others, he explains that a solar cell converts energy in the photons of sunlight into electricity by means of the photoelectric phenomenon found in certain types of semiconductor materials such as silicon and selenium. Performance efficiency of solar cells depend on temperature, insolation, spectral characteristics of sunlight, and so on. Table 2.02 summarizes and gives us a general idea of how much PV technology has improved tremendously over a period of 10 years in terms of efficiency, cost, and system life. High capital investment and low efficiency have limited the applications of PV systems in building industries before. However, PV panels have experienced 86% reduction in the cost while increasing in PV module production rate. The price for solar energy was around $25 per watt in 1970, which has dropped to around $3.50 per watt in the year 2010. This has been further reduced today to about $1.475 per watt of rooftop PV system in Germany that includes costs of BOS, or balance of system, which are the module supports, cabling, and power conditioning, as per the data in illustration 2.03. In the year 1990 in Germany, price for the same PV rooftop system cost an equivalent of almost $16 per watt as compared to the current $1.47 per watt. This gives us a net price regression of about 90% over a period of 24 years and is equivalent to an annual compound average price reduction rate of 9%. In an article, Furkan writes that the target is to further reduce the cost to $1 per watt or less in the year 2020. The PV cell productions in the world have increased from 10 megawatt peak per year in the year 1980 to 1,200 megawatt peak per year, or 1.2 gigawatt peak per year in the year 2004. Illustration 2.04 shows the trend of PV module production between 1988 to 2003. The current data shown is extracted from the Photovoltaics report by Fraunhofer and is updated on 26th of August 2015, whereby photovoltaics could be seen as a fast-growing market with a compound annual growth rate of 44% between 2000 to 2014. PV module production has increased rapidly. In 2014, China-Taiwan held the lead with a share of 69%. Europe contributed with a share of 6%, while Japan, USA, and Canada each contributed 4% respectively. The graph shows the global cumulative PV installation from 2008 to 2014. In 2014, Europe's contribution to the total cumulative PV installations amounted to 48% as compared to 58% in 2013. In contrast, installations in China, Taiwan accounted for 17% as compared to 13% in the year 2013. In a 2000 article by E.A. Alsima and others, the energy output of a typical PV system and its energy payback time, or EPBT, was studied. Two types of grid-connected PV systems, a rooftop system and a large ground-mounted system, and two module technologies of multicrystalline silicon and thin-film amorphous silicon are considered. System performance is assumed at a conservative ratio of 0.75, which means that 25% of energy losses occur. A conversion efficiency of conventional electricity supply system of 35% during the year 2000, which is the year of study, was used as a standard. Finally, three irradiation levels are distinguished, namely, number 1, a high irradiation of 2,200 kilowatt-hour per meter square per year, as found in the south-facing western USA and Sahara, a medium irradiation of 1,700 kilowatt-hour per meter square per year, as found in large parts of the USA and southern Europe, and thirdly, a low irradiation of 1,100 kilowatt-hour per meter squared per year, as found in Middle Europe, like Germany for instance. Given these assumptions, the study evaluated the energy payback time as the ratio of the total energy input during the system life cycle and the yearly energy generation during the system operation as seen in the illustration. We see in the figure that the EPBT for the study year systems is 2 to 3 years in a sunny climate and increases in 4 to 6 years or more under less favorable conditions. Also note that the contribution from the supports and the module frames is significant, especially for the ground-mounted systems. Regarding thin film technology, it can be inferred that due to their relatively lower efficiencies, the energetic advantages are partially cancelled by the higher energy requirements for frames and supports. An EPBT of 2 to 6 years may seem rather long, but in view of the expected lifetime of PV systems of 25 to 30 years, there is still a significant net production of energy. The net energy yield of these systems, assuming a 30-year lifetime, would be 10 to 14 in sunny regions and 5 to 7 under low irradiation levels. A first conclusion from these energy balance considerations can be that grid-connected PV systems already have a significant potential for reducing fossil energy consumption, although it may take a few years of system operation before these savings can actually be cashed in. This was in the year 2000. At present, depending on the technology and location of the PV system, the EPBT today ranges from 0.7 to 2 years. Rooftop PV systems produce net clean electricity for approximately 95% of their lifetime, assuming a lifespan of 30 years or more. Only a couple of decades ago, PVs were dismissed as a non-viable technology because the energy embodied in the manufacture of the cells was greater than the energy supplied by the technology over its lifetime. This has been the state of PVs in 1979. However, the rapid improvements in performance that have been experienced in the last 2 to 3 decades have changed this situation entirely, as the paper by Alsima and Euler in 2000 demonstrates. In the same article by E.A. Alsima, and as shown in this illustration, carbon dioxide emissions per kilowatt-hour of supplied electricity for grid-connected rooftop PV systems was shown. For purpose of comparison, a number of conventional power generation technologies are also depicted, with their status as of 1999 data. From a recent International Energy Agency study in 1998, the authors have furthermore included estimates for wind turbines and biomass gasification technology, as well as their estimate for the study year's multicrystalline silicon PV technology applied in a rooftop. The results show the estimated carbon dioxide emissions for PV technology are in the range of 50 to 60 grams per kilowatt-hour, which is considerably lower than fossil fuel plants, but higher than two competing renewable energy technologies. With improving technology, PV-related carbon dioxide emissions may become significantly lower, around 20 to 30 grams per kilowatt-hour in the near future, or even 10 to 20 grams per kilowatt-hour on the longer term, so that only in the last case can PV systems be at the same low range of carbon dioxide emissions as the current level of wind, biomass, and nuclear energy. It can then be concluded that PV systems are able to supply energy at a considerably lower carbon dioxide emission rate than current fossil energy technologies, but on the other hand, photovoltaics are still highly behind biomass and wind energy when it comes to CO2 emissions. In another article by V.M. Fithanakis and others in the year 2011, it was explained how material and energy utilization and recycling will continue to improve the environmental profiles of photovoltaics. A recent major improvement is a recycling process for the sowing slurry with the cutting fluid that is used in the wafer cutting. This recycling process recovers 80 to 90% of the silicon carbide and polyethylene glycol, which used to be wasted. Recycling silicon carbide and polyethylene glycol from silicon slurries decreases the EPBTs of these technologies. The illustration compares photovoltaics greenhouse gas emissions with those of conventional fuel-burning power plants, revealing the considerable environmental advantage of PV technologies. The majority of GHG greenhouse gas emissions are from the operation stage for the coal, natural gas, and oil fuel cycles, while the material and device production accounts for nearly all the emissions for the PV cycles. The greenhouse gas emissions from the nuclear fuel cycles are mainly related to the fuel production, like mining, milling, fabrication, conversion, and enrichment of uranium fuel. Current technology and trends based on today's rates and standards enabled a future forecast of energy payback time and greenhouse gas emissions for different PV types as per the illustration. The decrease is substantial, the forecast helpful in relaying a clear and positive message for PV systems. The article by Photovoltaics and Kim concludes very promisingly for photovoltaics, stating that the PV industry is striving for cost savings and simultaneously for advanced performance, which largely translates into life cycle energy savings and emissions abatement. The conversion efficiency, material usage, and production energy efficiency of both silicon and cadmium telluride PVs are improving rapidly. Thereby, we also expect the risks associated with the life cycles of PV systems to be reduced, and that frequent updates of these analyses are necessary to follow this evolution. Mont Cenis Academy in Germany consists of a huge microclimate glass envelope which forms the shelter for several of its interior buildings constructed in wood. It houses a civic hall, a hotel, a restaurant, a library, and leisure facilities. To prevent the exterior building from overheating in summer, a multifunctional PV system of 1 megawatt peak has been structurally integrated. The PV modules serve as the exterior building skin and allow at the same time shade, daytime lighting, and electricity production. All PV modules were assembled in a nearby plant 15 kilometers from the site. This project showed that BIPV successfully allows one to control the interior climate of a large microclimatic glasshouse. It is expected that the PV shading system will have a longer lifetime than conventional shading systems. Its multifunctional use makes it attractive and cost-effective. The system, though, is imperfect. The calculated energy output has not yet been reached. On the roof, although the PV modules are mounted with a slope of only 5 degrees, the sawtooth roof causes some shading on the PV modules in the early morning and evening, as well as in the winter, when the sun is low on the horizon. The effect of this partial shading on the total energy output has been underestimated. But in spite of such failures, the project is yet to be assessed based on a number of quantitative and qualitative, technical and social civic criteria. BIPV can be of the form of roofing materials, wall and fenestration materials, and flexible photovoltaic modules, and can be integrated to the roof of new buildings or where major roof replacement is undertaken. Methods of integration include exchangeable PV shingles, prefabricated PV roof panels, and insulated PV roof panels. When BIPV displaces conventional building materials, savings in the purchase and installation of conventional materials lower the net cost of the BIPV. BIPV walls, roofs, and awnings provide fully integrated electricity generation while also serving as part of the weather protective building envelope. BIPV can serve as a shading device for a window, a semi-transparent glass facade, a building exterior cladding panel, a skylight, a parapet unit, or roofing system. Norton B. and others explain in their article, Enhancing the Performance of Building Integrated Photovoltaics, that the adoption of BIPV can vary greatly and within, by country, depending upon climate, built environment, electricity industry structure, government policies, local product offerings, market stimulation mechanisms, consumer demand, existing industrial capabilities, and the forms of tariff arrangement for grid-connected PV power generation. It was also highlighted that modularity of BIPV results in short installation times, and the lack of moving parts reduced the need for maintenance. It was also pointed out that some countries with low specific land use per capita, such as Japan and some countries in Europe, preferred locating photovoltaics on buildings to specifically devoting scarce and precious land. Grid-connected BIPV feed electricity directly to an electricity network operating in parallel with a conventional electric source and do not usually require or use batteries. The performance of a grid-connected system depends on PV efficiencies, local climate, orientation and inclination of the PV array, load characteristics, and inverter performance. Oliver and Jackson in their article succinctly enumerates the benefits of grid-connected BIPVs as follows. First, PV systems integrated into or mounted onto buildings can avoid the cost of land acquisition, fencing, access roads, and major support structures for the modules. This is because the building on which the system is placed either provides or avoids the need for these functions at no additional cost. It would have been there in any case. A building is also likely to be close to the electricity grid, avoiding some cabling costs that would be necessary at a remote PV site. Secondly, PV systems on buildings produce electricity at or near point of use, avoiding transmission and distribution of electricity and the costs and losses associated with this. This argument is particularly strong for PV systems on commercial buildings where the demand for electricity, say from 9 a.m. to 5 p.m., typically coincides with supply of electricity from PV systems. Thirdly, PV systems that are integrated into the building structure can provide the function of protecting the building from the weather and avoiding the use of other building materials. The costs of the system can therefore be split between the functions of electricity provision and weatherproofing, reducing the net cost of the former. A BIPV cladding system provides two functions. Firstly, it produces electricity that replaces conventional sources of electricity, and secondly, it performs weatherproofing functions in the place of a conventional cladding system. In comparing BIPV systems to the alternatives, the function of both weather protection and electricity provision should be taken into account. Employing a BIPV cladding avoids the use of other kinds of cladding materials. It also avoids both the energy inputs and the economic costs associated with these other cladding materials. Thus, a comparison of energy and economic costs of BIPV with other electricity supply options should take account of, like subtract, the energy and economic costs associated with the avoided cladding materials. The two figures from the same study by Oliver and Jackson illustrates both the favorable and unfavorable sides of BIPVs. Illustration 3.01 shows the total primary energy input in megajoules per kilowatt-hour of electricity produced and distributed to the point of use for BIPV cladding systems compared with a centralized PV plant and the average European electricity mix. Firstly, comparing the central PV plant with a BIPV system reveals that despite the higher output performance of a central PV plant, less embodied energy is required per kilowatt-hour of electricity generated by the BIPV system. This is due to the significant amount of energy embodied in the balance of system component of a central PV plant compared to a BIPV system. In addition, there is no embodied energy required for transmission and distribution of the electricity from a BIPV system to the point of use, as it is assumed that the electricity is consumed within the building. Finally, if the energy embodied in a conventional glass cladding system is deducted as an avoided cost, the benefits of BIPVs over central PV plants and conventional sources is increased. Conventional electricity sources use significantly more primary energy to produce electricity and to transmit and distribute it to the point of use when compared with PV systems. This is mainly due to the low conversion efficiencies of converting thermal energy into electricity, which is typically around 35%. The next illustration, illustration 3.02, compares the unit electricity cost of PV systems calculated with an average European unit electricity cost. It also includes transmission and distribution costs. When comparing PV systems with conventional electricity supply in Europe, there is a trade-off between energy and economic viabilities. PV systems offer the potential to supply electricity in a manner that uses significantly less primary energy than conventional electricity mixes. The associated resource use savings and emission reduction provide a strong argument for the adoption of PVs. However, PVs applied in European locations are currently significantly more expensive than conventional electricity sources. Most systems installed today are heavily subsidized or not considered to be economically viable at all. The figure shows a study result for the energy payback period of a roof-mounted BIPV at different orientations, resulting to a minimum of 7.1 years for south-facing systems to a maximum of 20 years for west-facing BIPVs. It can be inferred from the study data and compared to current EPBTs of multicrystalline silicon and cadmium telluride PV modules that BIPV cost efficiency developments are still underway. High cost remains the major challenge when it comes to utilizing BIPV. Without state aids, subsidies, or incentives, prices remain high and impractical for implementation. In general, BIPV cost is much attributed to its modules and inverters at an average of 73% and 8% respectively, and the rest for BOS costs. The cost of a BIPV system can be lowered by reducing PV module and component manufacturing costs, installation costs, operation and maintenance costs, and improving PV and other component efficiencies. Considerable enhancement of BIPV system performance is, however, achievable without improvement in PV cells performance. Given that the latter has and will continue to improve, the prospects for a greater range of viable BIPV applications is promising. Incorporating PV materials into products such as roofing materials, windows, and awnings provides the opportunity for cost reduction by replacing common building materials with PV materials at marginal costs. Apart from energy benefits, BIPV offer design flexibility and aesthetic balance as compared to the traditional rooftop or ground-mounted PV modules. This clean technology and integrated system offers more aesthetically appealing design options and solutions, which can be easily assumed to be further developed and varied in the coming years. And given the dynamic nature of the PV industry and the expectations for future cost reductions, the economic benefit of BIPV system will bring forward the date at which grid-connected PV electricity supply in Europe and in the rest of the world to be considered viable. Thank you.